Because most mechanical property of materials will be characterized by axial loading. Let me give you a discussion on the ductile and brittle materials and their mechanical response. Okay, so let's first consider like a typical axial loading. So if you consider some sort of a cylindrical pillar or any other shape pillar, then if this pillar is under tension with the force P, then stress at this imaginary cut will be P over A, and the strain will be displacement delta L divided by L, right? So this will be strain and this will be stress. And as I told you in previous lectures, material property must be defined by normalized force and normalized displacement, which is stress and strain. And typical sigma epsilon curve of a ductile material is as shown below. So this is a strain and this is a stress. So in the beginning, you're gonna see like a linear relationship between strain and stress. Okay, and we call this as elastic regime. After some point, what you're gonna see is you're gonna see that it will deviate from this linear curve, and typically it will have some sort of softening, or this slope gets similar. Okay, and if this slope gets similar, and if you draw another line that is parallel to this axial elastic zone and with 0.2% of gap, and you can find some sort of overlap point, we call that as typically yield point or yield stress, sigma y. Okay, then after that, after yield point, what you're gonna see here is if you extend your material this much, it will not come back to its original shape. It will come back to deform the shape. Like imagine that when you have some like a metal clip or metal pin, if you try to bend the pin or deform the pin a little bit, you can see that it will come back to its original shape completely. However, if you bend your pin or clip too much, you're gonna see that it's not coming back to its original shape. Okay, that's a so-called plastic deformation, and this is occurring in this range. Okay, beyond this range, beyond this yield point, you don't expect it will be recovered completely. Okay, so after making this irreversible deformation and deformation, of course it cannot sustain the force completely, and it will have some maximum force defined by, here this maximum force is defined by P over A, and what you're gonna see here is at some point it will start to have some sort of necking behavior. Some point will be like become smaller and smaller, and you're gonna see final fracture of the material. This is typical stress strain curve of ductile material. Of course, when we define this P over A, you don't account for the change of cross-sectional area A. We said when typically in engineering stress strain curve, when you define P of A, even though some part of the sample start to having similar cross section, you still use cross sectional area A in the pristine state. Okay, if you account for the change of cross section, it will be actually showing ever increasing stress until the fracture. Okay, this is defined by P over A prime, and we call this as true stress. Okay, so true stress and engineering stress is identical at some point, up to some point, and when you start to see some sort of necking behavior, true stress and engineering stress, which is defined by initial area, true stress, which is defined by current smallest cross-section area, will have a different response. Okay, but we typically define the ultimate strength of material with engineering stress. But anyway, so these are the typical behavior of ductile material, and we call this initial range as elastic, second range as yield, and after some point you're gonna see increase of stress again. We call that as strain hardening regime. After that, some part gets smaller, we call that as necking regime. Okay, so please try to remember and take a look at the definition of proportional limit and yield strength and ultimate strength and etc. And typical example of aluminum, steel, and titanium alloys are given here. Yeah, you can see Young's modulus and yield stress and ultimate strength of these material. You can see that this titanium alloy, even though it's quite light, it has quite large ultimate strength. Okay, so let me see. Yeah, actually, I don't think the unit is right. This must be GPa. Yeah, these may be in MPa, megapascal. Yeah, please be careful about this. And as I told you, when somebody say some material is stiff and strong and tough, you now should have a very clear distinction. Stiff means high E. E is the slope in the elastic regime, is Young's modulus. When somebody says material is strong, it means the maximum stress, the ultimate strength is high. When somebody says the toughness is high, it means high integral from 0 to epsilon f and sigma dE. It's like what you can understand this is it absorbs large energy until failure. Okay, that's so-called tough. Okay, so please now have distinction between stiffness, strength, and toughness, or the words stiff, strong, and tough. Okay, it indicates different meanings in engineering sense, but in normal life, in everyday life, people mix these words. Okay. Now, the question you may ask is like, can we tune ductility of ductile material? And yes, yeah, we have done this practice for several thousand years ago. Okay, for several thousand years. Okay, so when you have like a bronze or 청동 in Korea, actually this is alloy between copper and tin, guri and 주석. Or in modern life, what you can see where you can find this bronze is the 유기그릇. Like when you go to in Gyeonggi-do, there are like a huge complex where people are making a lot of 유기그릇. Actually, 유기그릇 refers to the dishes made out of bronze or 청동, and that's what our ancestors have done to increase the strength of the copper. And regarding the steel, actually steel is not 100% iron. In addition to iron, you have to mix carbon atoms as a major like a mixing element. In addition to carbon, you have to mix like a silicon and other vanadium and other alloys elements. Okay, anyway, so the idea behind of mixing this other material is that by mixing these kind of other elements, you're gonna increase the strength, even though you're gonna sacrifice the ductility a little bit. Okay, so increasing tin concentration in bronze or increasing carbon concentration in steel, you will have increasing strength and decrease in ductility. And this is a typical behavior of ductile material. Okay, so if you're gonna major in metallurgy in material science, you're gonna learn about nanomechanical background behind why material property changes like this. Okay, so this is a short discussion about ductile material. In addition to ductile material, we have brittle materials such as rocks and glass. Okay, so for rocks and glass, we typically don't see necking, and without necking, and what you're gonna see is stress strain curve will have like a proportionality between stress and strain for entire range until the failure. And typically rocks and glass, they are weaker under tension. Under the compression, rock can sustain higher stress. I think it should be same for the glass. Okay, so this is a typical behavior of a brittle material. It does not have like a ductility zone, and it has like I would say it shows like a digital response. It will have recoverable deformation or complete failure. It does not have like a plastic deformation such that it has some bending, permanent bending that cannot come back to original state. Okay, so, and for this brittle material, the typical characteristic is compressive strength is much higher than tensile strength. Okay, so these are like a brief introduction about ductile and brittle material and their stress strain curve under tension and compression.